equilibrium of a rigid body. So here actually, first we will understand what is this equilibrium of rigid body, then actually we can go into the details. Now, here actually there are different terms, equilibrium and rigid body. So what it means for us is, first, what is a rigid body? Rigid body means, suppose if there is a body like this, and on this particular body, if I apply a force, then actually there should not be any movement of the individual particles of this particular matter, whatever may be the quantity of force I apply here. That is the understanding of rigid body. That means it shouldn't be deformed in any direction. So the body has to be strong enough to withstand this force. This force should cause only the movement of all the particles together with the same moment. But it shouldn't be like actually if I apply a force like this, then actually suppose if the body is deformed in this particular format, suppose if I apply the force like this, then actually if this is the case, this is not a rigid body. And the same body, if it is moving further like this, actually it moved. So from this location to this location, there is a movement because of the application of the force. But the dimension of the body. So by definition, a rigid body a physical entity whose dimensions will not change under the application of external force is called a rigid body. So why we define this separately is, so under the application of any force, usually there will be certain deformation of the body irrespective of the magnitude of the force. Usually even if you apply a very, very small force, then there will be a little deformation but may not be noticeable in magnitude. That means suppose if it is the order of a nanometer or a micrometer, then actually it's not appreciable, but still there is a deformation. Now for our calculation purpose, we assume that there is no deformation at all, zero deformation under the application of the force magnitude of any quantity. So this is how actually explicitly we state that the body is rigid. Got it? So this is the rigid body. And another, so why we are defining this as a rigid is, so here actually equilibrium of a rigid body. There is one more case actually what we are going to analyze, that is the equilibrium of system of particles. So there are two different cases. Now here actually all the particles of this particular body is treated as a single unit called rigid body. Now suppose if I try to apply two different forces on this particular body, and one force is applied like this and one force is applied like this. So this is F1 and this is F2. Now here actually if there is a movement of the rigid body from here to here, what it essentially means for us is, here actually the center of gravity is treated as the location of all the particles together. It is a single point called the center of gravity. Now this center of gravity is moved from here to here, assuming that this entire body is treated as a single point, so single point mass. So that means entire mass is focused at this location and the dimensions of this particular body is treated as a point. So this point is moved from here to here. So in that case actually we treat this as a separate case of rigid body. Suppose in this particular case, after the application of these two forces, Now actually the center of gravity is still again at this location initially. Even after the application of this force also, the center of gravity is not changing at all. But after the application of these forces, this one is getting moved to this particular direction. Now actually this is the new position after the application of this particular force. So this is the new position. And this one is the old position. Now if you notice in this particular case, here the center of gravity is actually doesn't change. Here the center of gravity is changed. So though it is a rigid body, and even here also it is a rigid body, here the center of gravity is changed because of the application of the force, and here the center of gravity is not changed because of the application of force. But if you notice, the rotation of this particular body is caused. That means, though the center of gravity is not changing, if you consider this entire body, rigid body, as a individual infinite particles, that means each dot is a point here. So this is made up of infinite number of particles. All the infinite number of particles are having certain amount of displacement from their initial location. But the rigid body actually is tilted like this, but there is no change in the center of gravity of that particular body. Now, here actually, for the analysis purpose, you cannot treat this as a rigid body. Individual particles you need to analyze separately. So this is called, so suppose actually if this body is under equilibrium condition, so we will study this topic as a separate topic called, so equilibrium of system of particles. So this topic what we are going to study here actually, so this is equilibrium of a rigid body. So this is equilibrium of got it? So these are two separate topics. So I hope you understood what is a rigid body, and then the equilibrium actually we are going to study now. So first you note down this. I am going to explain what is meant by equilibrium. So Vishal, so just actually I explained what is rigid body. Rigid body means, so the body actually whose dimensions will not change under the application of any amount of force is called a rigid body. Now the rigid body actually why we treat this separate unit is, in case of rigid body, entire body mass is located actually we treat as if like it is located at the center of mass, and the dimensions of this body is treated as a single point called zero size. So this entire mass is located at this location, and this mass is moving from here to here under the application of this force. Assuming that this entire body is treated as a rigid body, hence the entire body is moved till this particular point. So here actually we will treat this as a rigid body and try to analyze it. Even here also we treat as a rigid body, but for equilibrium cases actually we will be considering two different cases. One is equilibrium of body under, so equilibrium of rigid body, that is one case, and equilibrium of system of particles. Here actually in this particular case if you notice, under the application of two different forces, so this body center of gravity is not changed at all, but the body is rotated in this particular format. Hence actually every particle there is a movement, but the center of gravity overall actually there is no change. So hence if you wanted to identify the equilibrium of this particular body, you have to analyze all the particles individually and then try to understand whether the body is under equilibrium or not. So this kind of analysis what we call as the equilibrium of system of particles, and this kind of case we call as the equilibrium of rigid body. That means if you treat entire body as a single point, that is a rigid body, and if you treat entire body as infinite number of individual particles, that is called equilibrium of system of particles. Understood, Vishal? Any questions on this? You can let me know. So this is what we are going to study. Now what is meant by equilibrium? So equilibrium means, that means all the forces are cancelled out. That's what it essentially means for us. or in a single statement, even though if you are applying any number of forces, the final resultant is not moving in any direction, then we say that the resultant of all the forces together is equal to 0, then that is the system is under equilibrium. Now, equilibrium is defined as under the application of one or many forces if there is no linear movement and if there is no rotational moment to the rigid body, then we say that the rigid body is under equilibrium. That means here actually to test the equilibrium, so it is a must to have certain forces on that, and then all the forces should result zero displacement, both in linear and in rotational. So that is the condition of equilibrium. So that is as simple as that. Suppose if I have a body like this, on this particular body, if I apply a force like this of a magnitude F, and if I again apply one more force like this exactly in the opposite direction, but of the same magnitude, then these two forces, though these are acting on this particular body, will not have any linear moment for this particular body. So this is linearly equilibrium. That means no linear moment. Suppose actually if I have only one body and then there is only one force that is acting on this, then this will move. So this is moved to this location. Now in such case, the body is not under equilibrium. So this is the body is not under equilibrium condition in this particular case because there is a movement caused by the force. And then suppose only two forces are there and then the resultant is 0. But actually we are not very sure whether this body is rotated without changing the center of gravity of this particular body or not. In such case, we say that specifically this is linearly equilibrium. That means rotationally it may not be. So to check the validity of the equilibrium condition, you need to check both. So there should not be any linear movement and there should not be any circular movement also. Then only we say that the body is under the equilibrium condition. So the analysis is actually, so entire thing actually what we are going to study in case of statics is, so in engineering, civil engineering people will study this as the engineering mechanics. So engineering mechanics is the topic actually what we are going to study in this particular case of statics. So engineering mechanics actually, the entire study is, suppose if there is a dam that was built or a bridge that was built, it is made up of different rods, right? So all the rods are jointed together so that it can withstand the weight whatever is going on top of it. So for that, so the analysis has to be when all the forces including the mass that is there on top of the bridge, so all the forces together, if it is equal to the equilibrium condition, that means no effective force of the body, then actually we say that the body is under equilibrium condition. And that is the case what we need for the design purpose of that particular bridge. That means, suppose if there is two different pillars actually that are supporting a mass like this. So here actually, if there is a mass, or actually there is one body actually that is on top of it. So this is one pillar, this is one pillar, and this is one pillar made up of iron. Now this force what it is going to support here, this force is distributed in this particular direction, and this is distributed in this particular direction. Now the tension that was built on this particular rod is in the opposite direction to balance these two forces together. Now here actually there is no physical movement that is there. So this force is there on top, and this force, these two forces are supporting. Now if the body is under equilibrium condition at this particular point, that means this point is under equilibrium condition, then only it can withstand. Suppose if this force is in this particular direction, let us say, now actually less force is supported by this, less force is supported by this, and more force is supported by this. In that case, so there might be a case where this pillar can fail, right? So this pillar can fail in such cases. That means it cannot support anymore. That means the bridge will fall down like this. So here actually for the design purpose, we need to be analyzing this body is under equilibrium condition or not, this point is under equilibrium condition or not. So here actually physically there may not be a movement linearly, but because of this actually it might tilt like this, and then actually it will fall down. Got it? So in this particular case actually we are going to use this structural analysis, what we call as the statics cases, to understand whether bridge can withstand the forces or not, right? So this is what is the statics topic. In dynamics, that is completely different. Dynamics actually, because of the application of the force, there will be a movement, and then with what acceleration it is going, and with how much, so what is the speed of the particle, and then within how much time it is going to move. So all such kind of things actually we are going to study in case of dynamics. But again, the fundamental root for both the cases is only the force. Hence we study these two topics together as a single unit. Statics and dynamics, both are the effects of the forces. Got it? Okay. So now actually we are going to study a new concept called the moments now. So this is actually fundamentally coming from the fact that we have verified only the linear equilibrium for this particular body. Now for the circular equilibrium or the rotational equilibrium, we need to be defining a new concept called the moments of the force. So this moments of the force is nothing but, so in our general terms of physics, the moment of the force is nothing but the torque. So torque is nothing but the twisting force. So here actually this is linear movement it is causing. Here actually in case of moments of the force, if there is an effective movement, it can cause some circular movement, circular force. So that circular force actually will try to rotate the body rather than moving from one location to another location. So this we are going to study in detail, because this is a confusing part of this statics topic. So many people actually are getting confused at this particular location, and they feel that actually this topic is tough, but usually it's not. Got it? Understand this topic carefully. So a little bit of understanding of vectors is needed, which I have anyway covered earlier when I covered the cross product, right? So you note down this, I'm going to explain that concept. So movement of your force. Torque developed, so this is same as torque developed by the force. So both are one and the same. So these are actually the synonyms. So torque and the moment of the force. Movement is different and moment is different. So movement is nothing but torque. This is torque. But this is moving from one location to another location. So this is the different meaning, right? So movement of the force actually, so what we are going to calculate now. So movement of the force we mean here, so the torque developed by the force. Now essentially the force actually in case of linear movement, it will directly have an impact on the body. But in case of torque, it's not just only the force, the application, the point of application of the force also does matter. So essentially, the force actually has the characteristic of, one is the magnitude of force, and the second one is direction of the force, and third one is the point of application of the force. Now, so because of all these three effects, it will have the final effect on the body. So these are the causes for the effect. So that means force actually is made up of with three different characteristics. One is the magnitude of the force is nothing but with how much force I am trying to push this. So maybe 10 newtons, maybe 100 newtons, maybe 1000 newtons. That is one quantity which is essential. And another is the direction of the force. So even if you have 100 newtons of the force, so unless you put it in the proper direction, it won't have any impact on the body, right? So that means if you push in this direction, it will try to move in this direction. If I push from this direction, then it will try to move in this direction. That means the application of the force, the direction of the application of the force does matter. So to have an effect on the body. And next one is the point of application of the force. Point of application of the force, we mean here actually if you apply the force here versus if you apply the force here, it will have a different kind of effect, right? Obviously it will try to push the top part, it will try to push the bottom part. So bottom part will try to take the entire body, but top part actually if you apply more force, it will try to rotate rather than the movement, right? So here the point of application of the force also is very, very crucial. Now essentially this point of application is more important in case of torque or in case of calculation of the movement, right? So here, so suppose if you want to calculate the movement of your body, torque actually by definition what we have defined this as, torque is equal to R cross F is the torque. As I told you, torque is nothing but the twisting force. So twisting force is called as torque. Now force will have a direct impact of linear movement. Torque will have an indirect impact. That is, it will try to rotate the body without changing the center of gravity of that particular body. Now this force is called as, the torque is nothing but the twisting force. Here actually whatever the force quantity that is having effects on the body in case of linear movement is exactly equivalent to the quantities that are having in case of circular movement. There is one-on-one analogous to each other. For force actually, so this is the torque. Force will cause linear movement. So linear displacement this will be causing, and that circular displacement this will be causing. So linear displacement usually called as x, and the circular displacement usually called as theta. That means if this is causing a displacement of x, this will cause an angular displacement of theta. Suppose if this is causing velocity of v, this will cause an angular velocity of omega. And if this is having a velocity acceleration of a, this will have an angular acceleration of alpha. And here actually for the calculation of the displacement, so we have, so x is equal to ut plus half at square in case of physics. Now here actually exactly the same thing it will be there. Theta is equal to omega into, so omega naught into t plus half alpha t square. This is the angular displacement what we are going to calculate. So for every quantity in case of force, there will be equivalent quantities in case of torque, right? So these are actually 100% analogous. Now we have F is equal to ma. So here actually, so for the mass actually there is an equivalent term called moment of inertia here. So I into alpha, this is the torque. F equal to ma, I into alpha. The analogous quantity for mass in case of linear is exactly equal to the moment of inertia in case of what we are going to calculate in case of circular movement. Got it? So these are the analogous quantities. Now actually this moment of inertia calculation itself is a separate topic for us. So the understanding of this moment of inertia, we are going to go in detail. So when we deal with the mechanics part of it, this moment of inertia is very, very crucial actually. So ideally, there is no importance in physics for the moment of inertia, but we brought into picture intentionally just because of the simple reason for our analysis to be very, very easier, as if like it is a normal analysis of linear motion. We have brought a new physical quantity called moment of inertia. Other than that, there is no physical requirement for this. So we wanted to do our analysis very easily by correlating the force and the torque quantities like this. So hence actually there is a need to define something called moment of inertia, which is an equivalent of mass here in case of circular movement. Got it? So everything is analogous here. Now, if this is actually causing the linear equilibrium, this will cause the circular equilibrium. So this is what is our topic now, what we are going to study. So this is actually very simple to understand. But this actually, what is this we need to understand? Torque is nothing but a twisting force which will cause an angular displacement. That means it will try to rotate without changing the location of the center of gravity. So both the effects together has to be nullified each other. Then only we say that the body is under equilibrium condition. So effective forces has to be zero and effective torques also has to be equal to zero. So this is what we call as the moment of the force. All the forces together, if it is having zero circular displacement, we say that it is circularly equilibrium condition. Now actually, how we are going to calculate? That is based on this particular formula, that is R cross F. So I am going to go in detail R cross F. First you note down this. Now here actually, suppose, so I have fixed this particular body. Let us say this is one rod. Now actually on this particular rod, I wanted to rotate this vertically. Then I have applied a force of magnitude at this location. This is point A. This is the force F. Now I have applied one more force. This is at point B, the same magnitude F. Now this one will have more twisting force, or this one will have the more twisting force. Which one will have it? So B is having more twisting force. That means what is the thing actually that is essential for us? One is the same force is applied at both the location, but this is having less twisting force and this is having more twisting force. Now the quantity does matters here. It is, this is RA and this is RB. Now RA and RB. So out of these two scenarios, RA is less than RB. That means R is essential for having more twisting force. So R is essential, it is having a direct proportionality impact on it. That means this is torque 1, TA is equal to RA into F and TB is equal to RB into F. So since RA is less than RB, so hence actually TA will definitely be less than TB. So TB will have more twisting force on this particular rod than TA. So R is important for the movement. So torque and movement are one and the same, I said, right? So this will have more and this will have less. So, and one more thing. Now actually the same thing, I'll give you a different scenario. Now the force is actually applied at an angle of theta. The same force but applied at an angle of theta. This is F and this is F. And this is point A and this is point B. Now actually, how to calculate the moment now? How to calculate the moment? So this is RA and this is RB. Here actually, because it is perpendicular to the radius, we have straight away taken R into F as the product. But here actually, it is not perpendicular. I have, so with certain angle I have applied the force. Now actually what will be the effective force? What will be the effective force which is essential to rotate this particular body vertically? So here actually, F, if I divide into two different components, one component is the horizontal component, that is F cos theta, and another component will be vertical component, this is F sin theta. Now F cos theta will try to drag it, but what we are interested in is the circular movement for this particular body. So this will cause this will cause the linear movement, and this will cause the circular movement or rotational movement. So this is the difference. So F sin theta is essential in rotating this particular body. F cos theta is essential in moving this particular body horizontally like this. That means it will try to move that position of this particular body to a different location. But F sin theta, by holding this point like this, it will try to rotate like this. So F sin theta is the twisting force for us. And this twisting force is also having an impact of this R also. That means essentially the torque what we are going to calculate here it is, so torque is nothing but F sin theta into R. So or otherwise F into R sin theta. F into R sin theta. Now R sin theta. So R sin theta is nothing but, so this is R, right? So this is angle theta. So R cos theta is this one, and R sin theta will be perpendicular to this one. This is R. This is angle theta. This is R cos theta and this is R sin theta. So here actually if you draw a perpendicular from here, now this length, this is R sin theta. Now here actually I have separated this F into RB into sin theta. Now I have written sin theta with R and I have kept F alone. Now R sin theta is nothing but always the perpendicular distance from the particular point, from the origin to the point of application of the force. Got it? So this perpendicular distance is nothing but R sin theta. Hence, the way we calculate the moment is force multiplied by perpendicular distance from the point about which we are calculating the moments. To the force. Got it? So this is how actually we will be calculated. So what is the question, Vishal? So this is actually the radius. Now this angle is theta. So if this is the angle theta, then this component of the length is R cos theta and this component of the length is R sin theta, which is perpendicular to this one. Now this one, it is having a distance of R sin theta like this. Got it? Sorry, this is R sin theta. R sin theta. Understood? So this is R cos theta and this is R sin theta. So the force and the perpendicular distance from there. Got it? Okay. So you can note down this. Done. Okay. So this is how actually we will be calculating the moment of the force. Moment of the force is nothing but the force getting multiplied by the perpendicular distance. Yeah. So this is also called as the torque. Okay. So and the next case is couple. So couple means always comes together, right? But of opposite polarity in nature. Now here also, if there are two different forces but of opposite sign acting on a body, it will definitely cause movement of a circular. That means, suppose if I have a body like this, and then I have a force like this which is acting downwards, and I have a force acting which is acting upward. So this is F and this is also F. Then it will try to rotate this particular body rather than having a linear displacement for this particular body to be in this direction or in this direction. So it will try to rotate this particular body about its center of gravity like this. So after the application of these forces, this scenario is called as a couple. So this is couple. Couple will cause torque on the body. So couple will cause torque on the body. So this torque actually we will be, and couple actually one more important case of couple is, so the moment is independent of the point of application. So the moment of the force of the couple is independent about the point through which we are interested to find out the movement. That means, so I will explain in detail this one. Let us take one particular point like this. About this particular point, how much angular displacement this is having. So this body is having, that's what we are going to calculate. Now, so this one, I considered actually, let us say, this is in this particular case. So these are parallel forces. So this is upward force and this is downward force. And let us say, this is point A and this is point B. So for a better understanding, I have drawn. So this is a simple case, horizontal one. Now, take this. So this is point O, and this is, so this is OA vector and this is OB vector. Now actually we wanted to calculate the moment of the force about this particular point O. Now this moment is nothing but, so actually there is one more important understanding while calculating the moments is, so here actually you need to understand the sign convention of the moments. This is very crucial. Now actually, suppose I have a body like this. Now actually, on this body, I have applied, so I am holding at this particular point, and then I have applied a force at this particular location. So this will cause an anti-clockwise movement. And the same force actually, if I apply at this location, this will cause clockwise movement. So the torque or the moment are always actually causing only the circular movement. It is essential to understand which circle it is. There are only two possible circles. One is the clockwise circle, another is the anti-clockwise circle, right? So that is the universal standard. Now here actually the force is applied at this location will cause a circular movement which is in the clockwise direction. The force applied at this particular point will cause a circular movement but in the opposite direction, that is the anti-clockwise direction. So if I apply two different forces by holding here, so same magnitude force actually if I apply here, this is F and this is also F, it will not cause any rotation for this particular body if you hold at the center of gravity like this. It will try to move linearly rather than rotating it, because the anti-clockwise movement and the clockwise movement both will cancel out each other. Hence, there is no circular movement, or actually there is no angular displacement for this particular body. So if you hold at this location and apply two different forces like this. So here actually, the way we calculate here it is, let us say this is R and this is also R. And this is also R. Now actually, so this is R cross F. The way we calculate here it is, from R to F actually draw a line like this. So R to F actually you draw a line like this. So then actually assume that this is an anti-clockwise, obviously, right? And then even here also you extend like this, and then actually from R to F actually you draw a line like this. So this is clockwise, this is anti-clockwise. If you add these two, that is R cross F plus R cross F, and this R cross F will be anti-clockwise. That means, so you need to apply a sign convention, then only actually you can calculate this to be 0. So the standard convention is the anti-clockwise movement has to be treated as positive and the clockwise movement has to be treated as negative. So here this you need to treat this as the minus. So the sum of all these things comes out to be 0. Then actually we say that this body is having no movement. That means no angular displacement it can cause for all these forces together. Got it? So this is the standard convention is anti-clockwise positive. And the clockwise negative. So this is the universal convention. Got it? So here actually, now assuming this convention, now there is a couple like this, two different forces that are acted on this. Now actually I am trying to identify the movements about a random point O. It's a random point. From this actually I am trying to calculate the angular displacement of this one, entire body. Right? Now for this actually I can calculate the moment of the force as OA cross F. So OA cross F actually, now this is F direction and this is OA direction. So the R cross F, this direction actually is the moment direction. That is, this is the clockwise. And here actually this is OB direction and this is the F direction. Now this is from R cross F actually if you calculate. Yeah. From R to F, yeah. So this is R. So this is in this direction, opposite direction, right? So this is OB cross F and this is OA cross F. Now this has to be treated as negative and this has to be treated as positive, anti-clockwise. So the sum of the movements, total movements for the couple, this is T is equal to, or actually usually it is represented with M. So M is equal to OA cross F. And this is OA cross F is negative and anti-clockwise, that is OB cross F. OA cross F and OB cross F is the total moment. Now here, if we expand this, so you note down this, I am going to erase it and then write it. So what is the doubt? So here actually, this is the force direction, vertically downward direction. This is R direction, right? So this is the angle between them. Yeah, this is anti-clockwise. So this is clockwise and this is anti-clockwise. Now here, the total moment of this particular problem is, so M is equal to minus OA cross F and then plus OB cross F minus OA cross F plus OB is nothing but this vector. This can be treated as OA plus AB. Cross F. Now minus OA cross F plus OA cross F plus AB cross F. Now these two will cancel out. Finally, we left with AB cross F. Now if you notice, this is independent of the point O. So this is what is my earlier statement. So whatever may be the point you selected, the moment is always same. AB cross F. AB is fixed and O you can take it any location. So the moments about any random point, if you take it, it is always coming out to be 0. So any random point here actually is very important for us. Why? Because so the moments about any random point, if you take it, if the moments are coming out to be 0, then only we say that the body is under equilibrium condition. Now here actually, suppose about this particular point actually there is no movement. Suppose if I take one more point here, about this particular point if there is a movement, then actually we are not very sure that this particular body is under stable condition or not. So we have to verify all the infinite points for the body to be under stable condition. So the movements about any random point, if you take it, it has to come out to be 0. That is the condition for the equilibrium. Got it? So for the body to test under equilibrium condition, so it has to be no linear movement, no angular movement. That means the sum of all the movements has to be 0. The sum of all the forces has to be 0. So for the body under equilibrium condition, the conditions for the equilibrium of the body. So one is all the forces resultant has to be 0. So this is condition number 1. And the second condition is the sum of all the moments has to be equal to 0. So then only we say that the body is under equilibrium condition. Got it? So these are the fundamentals. So I hope now you know that how to calculate the moments, because that is the crucial point. How to picturize the random point. So this random point actually, usually we take all the points actually. So all the points of consideration when there are joints. That means if we take point about this particular point, you can take point about this particular point, and if you take point about this particular point, we will check all the conditions for the equilibrium. Now when we solve some problems, right, you will get an idea how to solve it. And in that actually, we take the point where all the forces are passing through. That point actually we take as the crucial and try to calculate the all moments. And then try to verify that body has the equilibrium condition or not. Again, actually we take one more point and then actually try to calculate it. Got it? So whatever the points that are visible to us, about which we will be taking it. Got it? So that will assure all the infinite points. So I hope you understood a fair clarity on what we are going to deal in case of equilibrium of rigid body. And if you notice, the condition here actually, quote unquote, what we are going to deal with here, it is only, though if I am not telling explicitly, we are dealing with the equilibrium of forces in coplanar in nature. So all the forces what we are going to talk here are only the coplanar forces. I hope you understood by this now. So the forces that are acted on a single plane, we are trying to verify the equilibrium condition. But in case of 3D forces, it is not this simple. It will be much more complicated than this, because the torque calculation will go very tougher. So now actually we are talking about the rotation only in the clockwise direction and the anti-clockwise direction. What if there are 3D forces? Then can you imagine a clockwise and anti-clockwise direction? We cannot, because in all the solid case, like actually take about a sphere. In sphere actually you can draw it or you can cut a circle in any direction. So you can cut a circle like this, You can cut a circle like this, you can cut a circle like this, you can cut a circle like this. There are infinite number of cases actually the way you can cut the circle for a sphere. Now, in all the infinite directions actually we have to be verifying the moments. So that's why it is complicated. Now that is not as simple as like this. So we are calculating, or we are talking about the equilibrium of forces which are coplanar in nature. I hope you understood that. Got it? So one important theorem is, that is actually by common sense we can understand. So the sum of the resultant of the force moment is equal to the sum of the individual moments. So the theorem is, so as a statement you can write it, if a number of coplanar forces acting at a point of a rigid body have a resultant then the vector sum of the moments of all the forces about any arbitrary point of all the forces about any random point is equal to 0. Is equal to the moment of the resultant about that point. Now here actually, if there are multiple forces that are acting, now actually on a body, if there are multiple forces that are acting on this, now here actually you want to calculate the movement of this particular body about a random point which you have selected at this particular location. Now here actually there are different forces that are acting on this. Let us say this is F1 and this is F2 and this is F3. Now two different cases we will analyze. Now the effect of all the forces together will have a single effect on this particular body. That is, R is equal to F1 plus F2 plus F3. So this is the resultant force. Now for this particular resultant force, if I calculate the moment, so moment of R is about O is R cross F. So R cross capital R. So where capital R may be, this is the resultant form R, which is the resultant of all the three forces. So this is capital R. So now actually R cross F, this is the moment M. So M is equal to R cross, R is nothing but F1 plus F2 plus F3. So this is R cross F1 plus R cross F2 plus R cross F3. Now if you notice, this is M1, this is M2 and this is M3. So all these three are vectors. So M is equal to M1 plus M2 plus M3. So this is the theorem. That means if you consider this as a single force which is equivalent to all the forces together, then the moment of this particular force about this particular point is equal to the sum of the individual moments. So that is the theorem. That is, by common sense we can understand. Got it? So this is about the introduction of this particular topic. So in the next class, actually, I'm going to solve some of the problems based on that. So this is an easier topic. Try to understand the concepts clearly. Whatever I have discussed here, this is very, very crucial. Whatever I have discussed today is crucial. So rest of the thing is only the practicing the problems. Got it? So in the next class, I'm going to deal with all the problems. Yeah. So that's all for today.